Thanks a lot, Phil. It's a pleasure to be here. Everyone can hear and see my screen, right? All right.
Yes.
All right. Yeah, so I'm going to talk a little bit about atmospheric rivers and cool season flooding in the central U.S. From NOAA, the NOAA Physical Sciences Laboratory in Boulder. So yeah, honored to be here to share some of this stuff with you guys. So the agenda for the talk is pretty simple. I'm going to go into some background on atmospheric rivers and their links to precipitation extremes and flooding in the central U.S. I'll present, or for most of the talk, I'll be presenting a case study of a high impact event during late December 2015. And then I'll kind of wrap up by showing some composite results for AR events impacting the central U.S. So to start off, let's start really simply. What is an atmospheric river? It is, according to the AMS glossary, a long, narrow, and transient corridor of strong horizontal water vapor transport that is typically associated with a low-level jet stream ahead of a cold front of an extratropical cyclone. A bit of a mouthful, but these diagrams on the left kind of highlight that definition more or less. These are grabbed from paper Ralph et al. 2018. So they occur generally along the low-level jet ahead of a cold front, and they kind of reside in the warm sector of a cyclone. And I think beyond the nuts and bolts of the definition, I think the AR concept is a useful, at least from my perspective, useful for diagnosing the hydrometeorological impacts of extratropical cyclones. So ARs are often identified as regions of strong column integrated water vapor transport, or IVT, though most of the moisture tends to be concentrated in the lowest levels of the atmosphere. ARs are different from, but certainly dynamically related to and complementary to other components of cyclones, like your low-level jet, like your warm conveyor belt, etc. So just to start us off, I'm providing an animation here of IVT, this column integrated vapor transport quantity, as well as sea level pressure, to kind of give you an appreciation for how these features form, evolve in conjunction with extratropical cyclones in the northern hemisphere. So in general, these features are prevalent features of the extratropical flow and play a fundamental role in the global hydroclimate. So I'm going to let this play through, and just you can see how these features form, evolve in conjunction with cyclones, primarily or most frequently over the main storm track regions over the North Pacific and North Atlantic, but we also see them forming in and impacting the central U.S. in conjunction with cyclones that develop east of the Rockies. This is just an animation for December 2015 to give you an idea of what's going on with these features. So prior work has highlighted how ARs can impact the central U.S. and can produce extreme precipitation and flooding in this region. These are results from Slinsky et al. 2020, showing on the left the relative frequency of ARs for this long climatological period, 1981 to 2016. And then on the right, the fraction of daily precipitation extremes during this period that were, according to their methodology, attributable to ARs. So you can see on the left that these features are pretty common over the central and eastern United States, particularly in the cool season and transition seasons. So not as common during summertime. And we also see that large fractions, and in many cases, a large majority of precipitation extremes are attributable to ARs in the central and eastern United States. And accordingly, these ARs account for significant fractions of annual maximum flooding in this region. So these are results from Lavers and Viarini 2013, just showing the fraction of annual maximum flooding during 1980 to 2011 that were attributable to atmospheric rivers. So consistent with the results we saw before, large fractions, and in many cases a majority of the annual maximum floods co-occurred with atmospheric rivers, especially in the cool season. You can see the largest fractions are found in DJF in their results. So in general, ARs can support heavy precipitation when they supply water vapor to a region of ascent. That's a fairly basic concept, but extreme precipitation totals and flooding tend to result when ARs stall over an area for a long duration. And that's an idea highlighted in this sort of simple AR categorization scale that Ralph et al. 2019 devised. It's basically a phase space of AR intensity and AR duration, okay? And they basically indicate that those ARs that are the longest duration and the strongest tend to be the most hazardous. That's kind of not surprising. So I've constructed a kind of a poor man's climatology of long duration, intense atmospheric rivers using the ERA 5 reanalysis kind of in this region over North America. So this map shows the frequency of AR conditions that last for at least 48 hours with a maximum IVT value of exceeding 1,000 kilograms per meter per second. And this is just for September through May. So you can see these long duration, strong ARs are most common in the storm track regions of the North Pacific and North Atlantic, but we also see this poleward extending bulge from the Gulf of Mexico into the central US. This indicates that this is another region. The central US is another region that is susceptible to persistent and strong ARs. And a critical question that comes to mind, both from a research perspective and an operational forecasting perspective, is what processes govern these events. And to get at some of these processes, I'm going to be looking in detail at a high impact event that occurred during late December 2015. Some of you may remember this event. It was pretty big. So during this event, widespread heavy precipitation persisted for several days, resulted in extensive flooding across the central US. Also, there were convective storms in the southern US that produced severe weather. There are also many winter weather impacts across the southern and central US. All told, the event resulted in 50 fatalities and $2.4 billion in damages. So a really big event. This map just shows the accumulated precipitation during the event. And this map now that I've toggled on is from the USGS, just showing rivers that were above a flood stage in the black icons as of the 29th of December. So you can see these black triangles really highlight the very impressive spatial extent of the flooding that occurred during this event, with flooding occurring within this large swath stretching from northeast Texas all the way to the Great Lakes. So very impactful event, as there were significant impacts in the St. Louis, Missouri metropolitan area. Here's an aerial photograph from Union, Missouri, outside of St. Louis, just highlighting the flooding that occurred there. So to give you a full depiction of the synoptic-scale flow evolution during this event and the associated formation and evolution of the atmospheric river, I'm going to be showing an animation of a quantity called potential vorticity in the upper levels. So it's basically, if you're not familiar with this quantity, potential vorticity, it's basically just showing us a detailed structure of the upper level jet stream and associated troughs and ridges propagating along the jet stream. It could show geopotential height, but I like this quantity because it shows kind of the detailed structure of the waves propagating through the jet stream. I've also plotted the IVT in the warm colors and vectors and the sea level pressure. And I've also overlaid the hourly precipitation from the NOAA Stage 4 product. So I'm going to let this play through just so you can see kind of the evolution of all these variables with each other. Just letting it play through the end of December. Yeah, so basically as it starts again, I'll just point out some key features here. So the PV field shows the amplification of an upper level wave pattern, exhibiting the formation of an elongated, slow-moving upper-level trough that eventually becomes cut off. You can see there. And this feature is associated with the spin-up and persistence of a cyclone centered over southern Texas, and sustained strong water vapor flux within this elongated corridor, or AR, stretching from the tropics, which supported persistent, widespread, heavy precipitation over the central U.S. So looking at snapshots on the 27th of December, again, this PV field, this potential vorticity field, highlights the structure of the upper level wave pattern. It shows this highly distorted, amplified wave pattern exhibiting a process of Rossby wave breaking. And this upper level pattern is reflected by distortion of the lower tropospheric temperature field that's shown in the middle here in the shading at 850 hectopascals. And within this temperature field, we see the formation of a strong elongated front delineating cold air mass shown in the greens and a warm air mass in the warm colors there. So the formation of this frontal boundary is associated with the juxtaposition of cold air advection along northerly flow and warm air advection along southerly flow that's associated with this cyclone-anticyclone pair here. So the heavy precipitation, not surprisingly, is focused along this quasi-stationary strong frontal boundary here. And it occurs in association with ascent that's forced downstream of the upper level trough, as well as extending northeastward along the frontal boundary. That's shown here in the panel on the right. So within this synoptic scale pattern, we see generally that it also promotes a strong persistent water vapor flux in the form of an atmospheric river. That's shown in the left panel. And this AR, this strong area of strong water vapor flux, ensures this abundant supply of moisture, as well as it establishes conditionally unstable air in the region. That's shown in the middle and in the right panel in the fields of column on integrated precipitable water and surface-based convective available potential energy. So in general, we see in this pattern the elongation of the IVT and the associated moisture plume associated with the atmospheric river favors very widespread heavy precipitation along the front. So these various maps I've shown kind of indicate a favorable combination of dynamical and thermodynamic ingredients for heavy precipitation. So moving down in spatial scale, just showing these quick animations to really demonstrate the co-occurrence and linkage between exceptionally persistent water vapor flux associated with this atmospheric river and the continuous generation of widespread heavy precipitation. So showing the IVT field again in the grays now, and then the next red radar reflectivity mosaic on the left, and then the cumulative precipitation on the right. So you can see continuous generation of heavy precipitation along the front within this expansive quasi-linear region, with precipitation elements tending to move downstream in a line parallel direction with the prevailing southwesterly flow aloft. So in general, within the evolution of this precipitation system, we see these processes of backbuilding and training occurring, which ensures the persistence of heavy precipitation during the event. So these zoomed in maps now highlight just how the precipitation was focused in the vicinity of this strong low level frontal boundary. So the red contours just show 2 meter potential temperature. So you can see this strong frontal boundary this elongated frontal boundary with the heavy precipitation focused along and on the cool side of the boundary, and low-level convergence acts as a kind of a focus for the continuous generation of new convective and stratiform precipitation elements. So I'd like to wrap up the talk by just extending the analysis beyond an individual case study. And here I've constructed composites from the ERA 5 reanalysis for the top 2% of 3-day periods for this long time period, 1979 to 2021, with respect to the time integrated meridional IVT averaged in a box over the Gulf of Mexico and the South Central US. So I have, after removing overlapping events, I have 48 events, and I've constructed composites of 300 hectopascal geopotential height anomaly. On the left, the sea level pressure anomaly, and 850 hectopascal potential temperatures in the middle. And on the right, I have IVT and the IVT anomaly. So starting at the beginning of the 3-day period at T0 and moving forward, I'm just gonna march through until T plus 48 hours. These maps, I think, nicely depict the general synoptic scale characteristics we saw in the case study, in particular a high amplitude, slow moving baroclinic wave pattern over North America, which is manifested by a prominent trough ridge pattern aloft and a cyclone-anticyclone pair at the surface. And these features establish strong poleward flow from low latitudes that corresponds to the formation of this elongated atmospheric river structure. A critical aspect of these patterns that we note is that these circulation features exhibit a very slow phase speed such that they move very slowly across the US and promote the persistence of water vapor flux into the central US that can lead to prolonged heavy precipitation like we saw in the December 2015 case. So with that, I'm gonna just give you my conclusions here, kind of restating what I already said. So ARs frequently contribute to extreme precipitation and flooding in the central US. Extreme precipitation and flooding are favored when ARs stall for long durations. The sustained supply of water vapor from a persistent AR can support repeated generation of heavy precipitation over the same area. And we saw through the case study and the composite maps that these strong persistent ARs can form as an aspect of slow-moving high-amplitude baroclinic wave patterns propagating across North America. In general, the evolution of these flow patterns fosters the establishment and maintenance of the ingredients for heavy precipitation, of which an atmospheric river is one ingredient. So with that, I'd be happy to take any questions if we have time. I know we're running a bit behind, but thanks for listening and have a good day.